Hello everyone, my name is Emil Carlsson and I'm a PhD student at the Computer Science Department at Chalmers University. And today I'm going to talk about a work I've done together with my PhD supervisors, Devla Dubachi and Fredrik Johansson, and which is called Learning Approximate and Exact Numeral Systems via Reinforcement Learning. So why do language partition mental concepts into words the way they do? A recent influential body of work suggests that language is shaped by a pressure for efficient communication, which involves an information-theoretic trade-off between cognitive load or complexity and informativeness. This means that language is under pressure to simultaneously be informative in order to support efficient communication, while also being simple in order to minimize the cognitive load. One domain where this was recently explored is numeral systems, and Xu and colleagues show that numeral systems across languages reflects a need for efficient communication. And especially they considered three different types of numeral systems. One approximate system where the numeral words have an imprecise or approximate meaning. Exact numeral systems where exact communication could be done just in a restricted range of the numeral line, number line. And of course recursive system where it's possible to actually with exact communication express any number at all. What is left unaddressed in these works is actually whether there is a mechanistic explanation for how efficient communication arises. And that is exactly what we would try to address here. And we ask ourselves whether there is a computational learning mechanism that actually leads to efficient communication. And to be more precise, we showed in this work that efficient, approximate, and exact numeral systems emerges via agents interacting with each other using reinforcement learning. But before going into our model, I just would like to define what we actually mean by efficient communication. We measure communication cost of a numeral system as the expected surprisal in the system, which is a standard quantity in information theory and which has been used previously in other work in cognitive science. And it can be viewed basically as how surprised a listener would be by the fact that a sender used a certain word for a certain number, basically. And to measure the complexity or cognitive load here, we simply consider the number of terms used in the numeral system. So in short, an efficient numeral system should, given a certain number of terms, minimize the expected surprisal or the expected surprise. So now to our model. We consider a multi-agent reinforcement learning setup consisting of two agents playing a signaling game with a finite set of numbers and a finite vocabulary. And the game goes as follows. A number is sampled from the need probability, and the need probability here captures how often a sender has to refer to a certain number. The sampled number is then given to the sender, which outputs a probability distribution over the vocabulary and then samples basically a word from the vocabulary or a token from the vocabulary, which is conveyed to the listener. So given this token or word, the listener produces a guess of what number the sender was referring to, and then a joint reward is given to both agents depending on how well the listener was able to reconstruct the true number that the sender was given. So for the need probabilities, we actually consider 4 different need probabilities in the paper. 3, which was estimated from human data, and you can read more about in the paper how exactly we estimated these. And then we also consider a uniform need probability. Worth mentioning is that the power law need probability that you see here is estimated in the same way as Xu et al. Did in their paper, so we can actually compare to the results. And the number range that we consider here is actually 1 to 20, and the reason for that is that all of the need probabilities that were estimated from human data were actually exponentially decaying, and there was very little probability mass after 20, basically. So we decided to just consider the range 1 to 20. When it comes to the reward function, we here consider 3 different reward functions. One linear, one inverse, and one exponential. And these reward functions were chosen in order to model different pressure for how precise the listener's reconstruction of the number has to be in order to get good reward. And you can see here to the right how the reward depends on the absolute distance between the reconstruction and the true number. And we can see that, for example, for the linear reward function, there is actually a fair amount of reward for imprecise reconstruction, while for the exponential reward function, the the reconstruction has to be very precise in order to get good reward. So when it comes to our agents, we model each agent using Q-learning. And in Q-learning, an agent estimates the expected reward for each state action pair and then takes the action it thinks will yield the most reward. In our setting, this translates to, for the sender, that given a certain number, the sender estimates the expected reward for each word and then basically sends the words it thinks will yield the most reward. And for the listener, given a certain word, the listener estimates the expected reward it thinks it will get for each guess, and then just guesses the number that it thinks will yield the highest reward. And here we model each Q function or function of the expected reward as a neural network with one hidden layer and 50 hidden neurons. So now I will just walk you through exactly how an agent takes an action in our game. So from the sender perspective, given a number n, the sender applies dropouts to its hidden layer in order to get a smaller neural network. And dropout simply means that we, with a certain probability, randomly ignore some of the hidden neurons. So this introduces some randomness in our estimated expected rewards. Then after applying dropout, the expected reward are estimated for each number and word pair here for the sender. The sender then sends the word satisfying the highest expected reward. And the randomness introduced by dropout here encourages exploration, so that the agents won't always send the same word given the same number, so they will actually explore and try sending different words. And this can actually be seen as an implicit form of Thompson sampling, which is a standard and classic algorithm for handling the exploration trade-off in computer science. And it works in the same way for the listener, but then instead of given a number, the listener is given a word as an input. Now going back to our model, I would just like to repeat exactly how it goes. A number is sampled from the need probability and then given to the sender, which uses this Q-learning model that I described previously to pick a word to send, and this word is sent to the listener, which also uses this Q-learning approach to pick a number to guess on, basically. And then joint reward is given to both agents. And the agents are updated over a batch of the signaling game by minimizing the mean squared error between the reward that they predicted to get and the reward that they actually got. So, and this is used using the optimizer Adam, which is a version of stochastic gradient descent. So after the agents have played the signaling game for a certain amount of batches and converged, we would like to compute the resulting numeral system. And we do it in the following way. So we would like to estimate the sender distribution, basically. And this is done in a Monte Carlo fashion, where we, for each number, feed that number to the sender 1,000 times using different dropout masks at each time. And then we basically count how many times each word was used for that particular number, and that becomes our sender distribution. And then we say that if this distribution is not peaked, we treat it as an approximate numeral system. While, we take the mode of this distribution as the exact numeral system. And then to compute the communication cost, we simply plug this sender distribution into the expression for this appraisal, which I showed earlier, and we compute the listening distribution there using base formula. So now to some experiments. During our experiments that we ran, we used a maximum vocabulary size of 10, and this was chosen since the maximum number of terms used among the human languages considered in Xu et al. Was actually 10, so that's why we picked this to be the maximum vocabulary size. Worth mentioning here, though, is that our agents during training are allowed to converge to numeral system using fewer than 10 terms, and this will actually be due to randomness in the initialization of the neural networks, but also from the sampling from the need probability. So then for each combination of need and reward, we train 6,000 independent sender-listeners pairs. And we train each pair for 10,000 updates. And this was more than enough to make sure that they actually had converged to something in the end. And the batch size that we used was set to 100 signaling games. In the following plot, you can see how our agents performed when we trained them using the linear reward function and the power law prior. So this is term usage plotted against the communication cost. And here the lighter gray area is the convex hull of all possible exact systems which we computed using brute force. And the darker gray area here is actually the convex hull of all approximate systems when assuming the Gaussian model used in Xu et al. So what we can see here is that our agents, which are represented as the blue and the green line, and the error bars here are ±1 standard deviation. We see that they are near optimal with respect to the communication calls, so they are close to the frontier of the respectively convex hull. And we have also plotted some of the human systems used in Xu et al. Here, so we can see that actually they have efficiency which is close to the efficiency of the human systems as well. Worth mentioning is that for the approximate systems, for 2 terms, our agents are actually below the convex hull for the Gaussian model, which we use as a baseline for the approximate system. And this is actually due to the fact that our agents are not bounded to actually model the words as Gaussians. So if we change the reward function, so here we have the inverse reward function and the exponential one, we still see that our agents produces numeral systems which are near optimal and close to the communication efficiency of the human languages studied in Xu et al. As well. These results turned out to be stable when we varied the need probability or the prior probability, and you can read more about that in the paper along with some discussion regarding the different need probabilities that we considered. So furthermore, in the left plot here we have plotted the frequency of term usage among all the experiments that we ran, varying the need probability, and to the right here you can actually see the different need probabilities that we considered. What we observed was that for the more left-skewed priors or need probabilities, the agents tend to produce numeral systems using fewer words, and this points towards that it seems to be possible to be near optimal using fewer terms, while for the uniform prior, which is a flat prior, we observe that there is actually a pressure for using more terms. To give you a feeling for how these numeral systems produced by our agents actually looks, we computed the consensus systems among all the experiments using correlation clustering. So basically, what is the consensus system for each setup of reward and need probability? And here you can see the consensus systems for 5 terms using the power law prior. So on the top here we have the optimal system with respect to communication cost, which was produced using brute force. And here we compare to a human system called Cardild. And what we observe here is that our agents produces systems with some similarity to the human system and to the optimal system. When comparing to the human system, we see that the main difference seems to be that our agents produces something that is a little less imprecise in the lower region of the number line, especially for the linear reward. And this could be due to the fact that the linear reward function gives quite amount of reward even for very imprecise reconstructions for the listener. So to conclude, we have seen that reinforcement learning agents can, via interaction with each other, develop efficient, approximate and exact numeral systems which are near optimal in an information-theoretic sense, and that they have the same level of efficiency as human systems, and with similarities between the artificial and human languages. So this offers a plausible mechanistic explanation for the results presented for human systems in Xu et al. So that was all for me. I just want to thank everyone for listening, and if you have any question, I'm happy to try to answer them.